So let's get started. So let's record some black hole thermodynamics. So some of the part I didn't explain very well. So okay, let's little bit talk about black hole thermodynamics. Review thermodynamics. Okay, so first law. What is the first? Zeroth law. Sorry, zeroth law. To wake you up. What is the zeroth law? On horizon. Okay. So ideal proof is that the ideal proof. Sorry. Okay. So ideal proof is that you just need to compute some kappa square. Is something like a number, and I don't even remember. I think most like 1/2 plus minus. I don't remember. And then c nu. So this is the case, and you just take the along. If you take the along the Killing vector. So Killing vector xc. So if you take the xc mu, partial mu kappa square is equal to, okay, maybe let's do that one by one. Okay, so xc mu, ideal proof is essentially a kappa square. And if you apply this one into here, essentially what you get is r mu nu rho sigma and xc rho xc sigma and so on. And since it's anti-symmetrical on that exchange, this becomes 0. So that's a proof. So therefore, along this horizon, this is equal to 0. Okay. Along horizon or along Killing vector, but one point is that at one point is a two sphere. So therefore, you have to show that even two sphere along two sphere it has to be constant. But that can be done by just using this at this bifurcation point, so that the S mu partial mu kappa square is equal to also 0. Because I mean this one is something like roughly speaking something like this one, xc sigma rho, something like that, and xc is 0 at the bifurcation point. So therefore, xc equal to 0 at the bifurcation point. One case. Okay, and the first law I need to explain a little bit more. So dm is equal to dm is equal to kappa over 8 pi and dA plus omega h dj plus phi h dq, and then this can be written th ds plus omega h, and so on, the same. So s is equal to, of course, s is the a over 4, th is kappa over 2 pi. Okay, so if you compare with the first law of the thermodynamics dE is equal to TdS, what was that? PdV, and what was that? Plus mu dN. Okay, mu dN. Then really area is the area over 4 corresponding to the entropy, and the TH is the something called Hawking temperature, is proportional to surface gravity. Okay, fine. So this one, yeah, of course, I mean, too famous. So this is called Bekenstein Hawking entropy. entropy, so Bekenstein really like considered Bekenstein really considered early 70s. I don't remember 71 or 72. I don't remember. So if you throw the cup of tea into the black hole, cup of tea of course has I mean he's drinking water now. Anyway, that has some temperature, non-zero temperature. So therefore it has some entropy. If you throw it a black hole, it just becomes tiny amount of increase of mass. But if the black hole does not have an entropy, it decreases. So in total system, it decreases the entropy. Because I mean the water has entropy, but once you throw into the black hole, the water is going to become black hole. I mean it just add the mass of a black hole, but the entropy is gone. So that's a simple, very Gedanken experiment what Bekenstein did in early 70s. So therefore, Bekenstein predicts that the black hole should have an entropy, which is proportional to area. Anyway, so that's the first what they did. That's why it's called Bekenstein-Hawking entropy. And then from the derivation, so from now on, so since this is the thermodynamics, and then so we know that this thermodynamics to go to the thermodynamics to statical mechanics, entropy has something called Kb, Boltzmann log of number of states. Number of states. So this is a microscopic understanding of entropy, and so from here to here, so this is the oh my goodness, I cannot write that. Okay, anyways, thermodynamics, and then this is statistical mechanics, microscopic, and this is macroscopic, and this is microscopic. So we want to understand like this way. So is there any way to understand this? This is a very big program, still like ongoing research, lots of things going on. And then to do that, first we need to introduce so-called a QFT, in curved space-time. To understand a microscope, understand a black hole, we need to introduce. That's a motivation from now on. Yeah. So before going that, so last time I tried to derive this one by so-called physical process. So I just anyways, physical process. So that is the constant curve, and then you have the Auger sphere. And then you have the R plus, and then R0, Auger sphere, and then you throw away the something in here, and then you just consider this is the tangent vector is something like xc, and xc is equal to what's the notation? Phi t plus omega h phi phi. So that's the you just throw the something into the curved black hole, and what's going to happen in the change of mass and angular momentum. So that's we try to evaluate last time, and then eventually what we obtained. Okay, so let's recall the following. So at the horizon, so delta m is equal to minus n and dv, and then d square y, and then square root h k dot j. So I just need to recall what's the notation. I mean, it's not bad idea to recall, because I mean I always go fast. So h k dot l. Okay, so I haven't changed the notation. Last time I called it this one is capital K, but which is not good notation K L and O. Let's see P. Let's use P. Yeah, let's use P. Okay, P. So the P is the I didn't change the notation. Sorry about it. Is that the TAB. So sorry, this one you call it U plus phi HM. So U is UA is the time vector, and then MA is the angular momentum vector. So that's the angular momentum vector, and this is the case, and then L is equal to what was that? TAB and then MB. So that's a notation. And then, of course, the block or maximum extended one is something like a something like this one. Yeah. So okay, sequence of diamond. Curve is sequence of diamond, and then you have something horizon is here. Singularity is here. And then here is the R plus horizon, okay, and then R plus horizon and R minus horizon, something like this way. And then we call it the C is a Killing vector here. C is a Killing vector, and C is always written is the kappa V delta V. LV, and the K is the affine vector. K is the like this one. Then V is the affine parameter at horizon. That's the notation. That's the notation, and then we derive this the change. So change of once you throw away this matter into the curve black hole, change of mass and change of the angular momentum is just given by the sum product with this K here, and then how to say the energy vector and the angular vector of the matter. So that's what we did, and then we just did some manipulation. For instance. Okay, anyway, so down M is equal to minus N dV d square y square root h. So K is just P is this one, so therefore we just have a TAB K A UB like this way, and then just you just need to manipulate. So if you manipulate this one, so this one, K is U is something like what was that? CB minus omega H and B. So therefore, this can be written. So let me erase here. So this can be written as follows: del N dV d square y square root H TAB KA KB kappa B, and then minus omega H dV d square y square root H K dot B. K dot L, sorry. K dot L. Okay, and we know that this one is equal to del J. Okay, del J. So therefore, Okay, so therefore, so delta m minus omega h del j is equal to kappa over 8 pi and dv d square y square root of h and then b rab ka kb. I just used the Einstein equation to change the stress energy tensor to the Ricci tensor, and this is equal to actually minus anyway. Okay, minus g. Okay, so that's the case. And then so Raychaudhuri equation, and then we plug in the Raychaudhuri equation. So d theta of dv is 1 minus r. I mean, you just have like a theta square over 2 plus, minus sigma square. Yeah, I don't remember. Plus omega square. No, I don't print out everything. And minus RAB, KA, and KB. So that's the Raychaudhuri equation. New Raychaudhuri equation. But we know that the theta at the static stationary black hole, theta equal to 0, sigma equal to 0, and omega equal to 0 at the horizon. But we now throw away some matter into the black hole, so there's a perturbation. Okay, so therefore the theta after throw away the matter, theta has the order epsilon. Theta has the order epsilon. So this is theta, my theta, and this is the order. So sigma is also like this, and the omega is also order epsilon. Like in the first perturbation order. So we just throw a tiny matter into a curved black hole. That will just break some stationarity. Okay, but it's a small perturbation. It's the first order perturbation. But since those terms are orders square term, so therefore those term is just order epsilon square. So second order perturbation. So we can ignore. Okay. So therefore d theta dv is minus RAB. So we just need to plug that one into here. Okay. Yeah, so that's the case. If you plug that one into here, so this part I lacked some explanation. So if you plug that into here, so the del m minus omega 8 del j is equal to minus kappa over 8 pi. Like this way. And if you just integration, so you get the minus kappa over 8 pi and the d square y, and then infinity square root h plus b d square root h dv, and then times theta dv. So that's what we have. And then what we do is that since it's a perturbation, okay, I mean here again you just use something. So you just throw away curved black hole into some matter like this way. Anyway, so it's okay, just schematic. So just matter here, then black hole become fatter. So black hole become a little bit fatter like this way. So I just be in schematic, like this way. Okay. But b equal to 0 is stationary. B equal to infinity is stationary. Okay, stationary. So therefore this term is gone. So stationary at the horizon, theta equal to 0. Okay, theta equal to 0 at the horizon. This term is gone. Okay. And then what else? This theta is also theta. is so this part is the what I have didn't explain very well. So theta is in fact obtained by just the trace of HAB, kappa AB, like this way, or kappa AB. Kappa is an extrinsic curvature. Extrinsic curvature is, as I mentioned many times. Maybe it's better to repeat. So if you have a hypersurface, and you have a normal vector, and then I have some normal vector, NA, and if you just move this one by parallel transport, okay? If you do a parallel transport, like this way, so the delta NA will show up. So this extrinsic curvature will just measure how they are different, okay? How they change the. Okay? Essentially, this is the quantity, and which can be just derived by just 1/2 HAB DHAB divided by dV. Okay? So it's now the hypersurface is the horizon. We are looking at the horizon here. And then at the horizon, the delta V is tangent also, both tangent and then the orthogonal. So therefore, we can just take a derivative with respect to V to get the extreme curvature at the horizon. Okay. And then this one can be written. I mean, so this can be written is like a 1/2 trace of, how to say, H dH dV. So H. So here I mean the H is the matrix. H is a matrix, and so there's a well-known identity that the 1/2. This is the 1/, determinant of H, and the D determinant of H dV. So that's the. So from this step to this step, do you know that this step? This often happens in the quantum filtering and so on. Do you know this step? I mean, maybe I can just explain. So suppose H. So here H I treated as H is a matrix. Okay. So of course H is an induced. H is an induced metric. HAB is GAB plus NA NB. So this is an induced metric on the hypersurface. And then suppose H has some. Suppose let's consider simpler setting. So it's BA1. I just diagonalize. So it's a symmetric matrix, so you can diagonalize like this way. AN, like this way. So then, what was that? This quantity is just a it's just A1 plus A2 plus plus AN. Do you understand what I mean? Is it okay? If you take a derivative of this one, you have a A1 times this one, A2 times this one, AN times this one. And if you multiply inverse metric, sorry, this is inverse metric. If inverse metrics, these exponential cancel, right? And take trace, you get this one. Okay. On the other hand, if you take a determinant, you just have the e to the b a1 plus plus an, right? If you take a determinant, just multiply them together, and take take a derivative, you get this one, right? You get this one, and the inverse matrix cancel this guy. So therefore, this is the simplest way to see that. And this one is in fact equal to small over square root h d square root h dv. Now here h means determinant. It's just standard notation of the GR. Okay. H is a determinant of metric. Okay. Here I treat it as a metric. Okay. Maybe I should use a different notation, but anyway. Okay. And here we know that this guy This guy is the proportional to first order perturbation. First order perturbation. Okay, so the set is first order perturbation. And d square root h dv is also first order perturbation. So therefore this becomes the proportional to order epsilon square, the last term. So this is proportional to. Okay. So we ignore this term, and you just need to evaluate this one. And if you evaluate this one, what you get is that essentially this one is equal to, this one is equal to. Essentially what you get is square root h, square root h. Just do that. dB and ddb will cancel, and then what you get is the kappa over 8 pi del A. Okay. So that's how you derive. So the last time I omit this step. I didn't explain this step. So I omit this step, so I just need to remind you why theta can be replaced by like this. Okay, so that's the difference between the change of the mass and the change of angular momentum. In this linear combination will give you a change of area with the surface gravity as a constant. So this is the derivation of the first law of the black hole thermodynamics without Q. Without Q. With Q, I mean, I just derive it by using Kerr-Newman metric. So that's the case. So what is the third law? What is the third law? The third law. So third law is the kappa. This is achieve finite many process, or what was that? Finite time, finite proper time. Okay, so this one kappa is surface gravity. So that is the same for well, I cannot just bring the temperature goes to 0. This is the thermodynamic statement. And then last time I used some so-called how to say? I already forgot. Badia metric to using the how to say rational Nordstrom black hole, and then we just consider so-called Badia metric. So which is something like suppose you have something like a let's see. The physical rational Nordstrom. Right, physical rational Nordstrom. I don't remember how to draw, to be honest. Yeah, this should be okay. Yeah, this should be okay. Like this way, and then there is a matter. Star is charged with star here. Okay. And this is a horizon. This is a horizon R plus, and this is the horizon for R minus. And we just throw some matter, some chunk of no ingoing, no ingoing fluid, and then we just consider the matter. The metric is something like 1 minus mr over r and plus r squared. Sorry, q over r, r squared, d sorry, I don't remember the detail. I didn't also print out this one. dv square, yeah, so it's not RB. It's B, right? Oh yeah. RB, B square, and R square. And then dv square plus 2dv dr plus d omega. Yeah, like this way. So we assume this metric R square. And the B coordinate is essentially this B coordinate in here. Okay. B coordinate here. And the B equal to B0, B equal to constant B0, so you throw away some no ingoing fluid. And then using weak energy condition, so which is TAB, UA, UB is like this way. So this is equality only achieved when U equal to for U is the any timeline curve. And then what we did, what I showed is that the last time I didn't have some time to explain so much. So using the weak, how to say? So weak energy condition. So I just derived this one. And then Q, right? As far as I remember. M dot. This dot is, of course, M dot means dm dB. Okay, like this. Dm. So I just derived this one. And then, so what I meant is that so this one, so at the, if you achieve the finite time by just finite time is just throw away null and achieve this m is equal to q. So this is the extrema case, extrema. So which is kappa equal to 0, Then this condition will really become something like a m times m dot minus q dot is greater than 0. Like this way. But now, so this means that since m is positive, m dot q dot has to be positive. Has to be positive, always, like this way. M dot q dot has to be positive. But once you achieve this, the extrema at the finite time, this condition is no longer satisfied. Because I mean, no extrema means like this way. Okay, no extrema is m is greater than q. Or of course, I think I should use q. But from here to here, to achieve that, m dot q dot has to be negative, right? Has to be negative. Okay. M dot q dot, because if it is the m minus q is positive to the is equal to 0, its derivative needs to be negative, right? But if it is negative, this condition is no longer satisfied. So therefore, so this violates the weak energy condition. So to derive this inequality, one has to use this weak energy condition. So that was the argument. So therefore, you cannot just throw away this. So this is one example of this third law. It's not proof. It's not derivation, but one way to argue to see the example why third law should hold. So we just no ingoing fluid, just throw a new ingoing fluid and just assume the weak energy condition. Then there's no way to achieve extrema black hole. Extremality from the just no extrema case. So those are the quick review by using half an hour I just explained the rough idea what I explained last time. So since it's important, black hole thermodynamics. So this is the highlight, one of the highlight of this course. Okay. So these are, yeah. Okay, so this the four law is these four laws are discussed by Bardeen, Carter, Hawking in '73, as far as I recall, '73. This fourth one, like a third law, was proven by Israel by '86, as far as I recall. So it's a later time. It's I mean, if you look at this Bardeen, Carter, Hawking paper, the third law is just derivation is difficult, but I mean, it's natural to assume third law, something like that. It's natural to assume third. Okay, so those are the one of the how to say highlight of the. Okay, so this is the. I would say pinnacle of the GR. Oh, one of the pinnacles, the highlight, one of the milestone. Okay, milestone. Of the GR. GR. So from here, so the from this. From this law, so we can just treat like as a black hole of the thermodynamics quantity, thermodynamics quantity, object. So it has a temperature, TH, has a kappa over 2 pi. Okay, kappa over 2 pi. So they want to have a like a temperature, so is there some thermal radiation? From black hole. I mean, you learned the thermodynamics, so like that's what Planck first found to show that to introduce H bar and so on. Anyway, so if you have a temperature, you have a Planck distribution of the thermodynamic radiation should have. So then how to derive this one? So this one is famously given by Hawking in the 74. Okay, 74, and which we are going to cover. Okay. So to do that, we need to introduce so-called QFT in curved space-time. Before that, there is something very interesting thing Unruh effect. Unruh effect. This is also the very typical like a phenomenon in QFT in curved space-time. So observer, so it's called observer is an accelerated observer. We'll see. Particle creation from vacuum. Okay, I would say Minkowski or some other vacuum. Okay. Okay, so that's what we are going to see from now on. Okay, before then, let's do some preparation. So okay, maybe I just explain. So there's a so we know that the Rindra space U and the B, and then so this is a Minkowski. Like this way. So this is Minkowski space, but we know that there is some change of variable. One can just move to this one is equal to kappa x dt square, x square. I don't remember that detail. Yeah, kappa x square minus dx square, where the u is equal to minus x e to the kappa t, and then b is equal to x e to kappa t, like this way. Okay, and then so you just consider some accelerated observer, which is x is constant. X is constant. Okay, so then this observer has a vector c, which is the b del b minus u del u, like this way, and times kappa as far as we recall. Okay. This is equal to, of course, del del t, because I mean this is x is constant. And we derive this observer. So this is called Rindra observer. Okay. So we derive this acceleration is in fact around the horizon, near horizon. So it's around the c del. It's just acceleration can be measured like this way. It's roughly kappa c nu. So that's what we saw a long time ago by Rindra space. Okay. Sorry, I told you wrong. So this is not, this is B, this is U. Okay. And at the horizon is U equal to 0 and U equal to 0. Then this is equal to equality. Okay. Equal. That's what we saw. And this observer has acceleration, but in fact, so if you just consider that the observer which is accelerated along this how to say curve, then this observer somehow receives some lots of particle creation, even though it's just Minkowski space and it's a if you just consider vacuums, for instance, if you just consider n 0 and 0, this is non-zero. N is a numbering operator in the QFT. So that is called the Unruh effect, and more precisely, it has kind of this like particle creation has like some thermal distribution, whose temperature is kappa over 2 pi. Kappa over 2 pi. So that is called Unruh effect, and we are going to see from now on. We are going to derive this Unruh effect. Any question at this moment? If not, I will. Okay, I will move on to the just do the preparation before going to talk about the Unruh effect. Okay, so let's consider some Klein-Gordon field in curved spacetime. Field, scalar field, or scalar field, in curved spacetime. Okay. So action is given by just here I just consider d dimension. Whatever dimension is okay actually. Okay, and then so okay. So this is a Klein-Gordon action, and then of course we know that the Klein-Gordon equation is something like this one. And then this one, in curved space-time, it becomes like this way. Okay, and we introduce some metric. So we introduce some metric on the field. So this is called inner product on a field product. So it's something like this one, f and g of sigma, which is I d s mu f star of x portion mu g of x portion mu f star of x like this. Like this one. Okay, so that's the inner product. We introduce in the okay. So then, if you consider the so here f and g can be understood as a solution of the Klein-Gordon equation. So this is the Klein-Gordon equation. And here we just consider sigma is some special surface. Whatever is okay. Let's consider global hyperbolic. So therefore the cosy surface is there. So it's some sigma or sigma prime. Whatever is okay. So okay, so then so here, so if you consider some current of the current in the Klein-Gordon equation, Klein-Gordon field, like if you consider current like this one, f star of g dot g, then so we know that this one will be conserved if f and g are f and g are the solution of the Klein-Gordon equation. Then so this inner product is independent of the choice of sigma. So this is independent of choice of sigma. But so this can be just integrated over this region V. So V dV, the volume, down mu J mu. So take their concept. And they just use the Stokes theorem to show that the ds mu, J mu, this is f dot g sigma minus f dot g sigma prime. Okay. So, so if you just use this inner product, if you use inner product, and then so just integrate over this current conservation around this p. If you use the Stokes theorem, this one is coming from sigma, the other is coming from sigma prime of inner product. The difference because of the normal vector is opposite. So therefore, opposite means that like this. Sorry, normal vector is opposite. So therefore, you have a minus sign. And then current conservation tells us the inner product is independent choice of sigma. This is sigma prime. Okay. That's the proof. Yeah. So this current conservation is okay, right? Because I mean, if you apply del mu on here, you have a del f, del alpha, del g, del alpha, del g. Cancel, or del acts on here, and del acts on here, and if you use the Klein-Gold equation, you get the cancellation. Okay. So here we assume f and g a solution of Klein-Gold equation. Okay. So this is so therefore this is like a nice inner product on a curved spacetime. So it's independent choice. Okay, and then G and F, so this satisfies, so you can easily check star, and then F star, G star is equal to I mean, this is just an exercise. I mean, just so this satisfies these properties. This is just a simple exercise to use a definition. Okay. And then now we just introduce orthonormal prime. Orthonormal modes phi I such that the phi I, so I is some whatever index. Phi I, phi j is given by delta ij, and the other is the phi star. So this is equal to minus delta ij, and then the cross term will vanish. And so on. Okay, so that's the. So we introduce some orthonormal modes. So okay, orthonormal mode, and then they expand this field phi of x. I mean, it's just a Fourier transformation. It's just a curved space version Fourier transformation. And then do the canonical quantization. Okay. Canonical quantization. I mean, in canonical quantization, there's two ways to do that. I mean, the honest way to do is introduce the conjugate variable, essentially the pi variable, pi of x, which is the, how to say, del L, del phi dot x, like this way. Just introduce conjugate variable, and then you just introduce like this way. And then equal time footing, y, sorry, not pi. And then is equal to I delta, what was that? X minus y, 3 or something like this one. So this is the canonical quantization you just do in the free field. And the other vanish, or like if you do the conjugate, this you get the plus minus sign or something like that. I'm not gonna write down everything. Okay. And this is canonical quantization. Quantization. Okay. And then this will lead, if you use a Fourier transformation, so if you do the this orthonormal property of this phi i's, so one can just show that the ai, aj satisfy Heisenberg algebra, delta ij, and then the other is 0. A is equal to 0 is equal to a dagger is equal to. I'm not going to write that. Okay, so the results are so therefore one can just consider this is creation operator, and this can understand annihilation operator. Okay, and then vacuum is defined usually like this way for any AI. For any I. So this is a definition of vacuum. This is definition of vacuum. So it's the standard story we learn in quantum field theory. Let's do an example. And then, yeah. So the function, so the 2-point function or Feynman propagator, whatever you call it, is 0 t phi x, a 2-point function. Okay. And this can be written sum of I phi ix phi star ij y, and then it's conjugate. It's conjugate. I'm not gonna write down everything. So you just conjugate means essentially you just change the role of x and y, or conjugate and conjugate. Okay. Fine. So those are the 2-point function or Feynman propagator, whatever you call it. Okay. Analogy. I mean, this one. I mean, we already learned. I think you guys already familiar with. I just make you get bored. But okay, let's quickly review the Minkowski spacetime. Okay. So Minkowski spacetime, and then in this case the f. I mean, okay, I don't know how much I should mention. I mean, it's just a parallel. I mean, if you just sigma is equal to the how to say, the t is constant surface. T is constant surface. Constant surface f and g is the something like is sigma d and q. I mean, I think for you guys it's too easy. this way. So those inner product we can introduce. And here F and G are the solution of usual Klein-Gordon equation. And under this inner product, so this phi k omega k is equal to k squared plus m squared. Okay. Square root of. So this is the orthonormal frame. Orthonormal frame. Orthonormal. I think this is called positive mode. Positive mode in the positive energy positive energy mode. Positive energy mode. Whatever you call it, it's totally fine. I mean, in QFT in cube space-time positive energy mode. So this is positive energy. So this corresponds to the ReDV. In flat space-time, this guy corresponding to this guy. I mean, just Fourier mode. Fourier mode. The phi star is most likely called negative energy mode in this QFT in space-time. I mean, just standard story. Standard story. I think everybody's familiar with here. But anyway, let's do that. Okay, so I mean, okay. Okay, so this is a model expansion. Model expansion Klein-Gordon in scalar field in flat space. This is positive mode, and this is positive energy mode. This is negative energy mode. And this is creation and annihilation operator, and which satisfy these conditions. It's really parallel. And then, of course, we know that sorry, maybe I just make you get bored. It's something like delta k minus k prime. 3, and the rest is 0. And green function is g of x, y is given by theta x naught minus y naught. And then dq k, to omega k, and e to the I k x minus y minus omega x0 minus y0. And then the other is something like its conjugate, y0 minus x0. I mean, the same. E to d. I mean, it's just minus of this ik of this. Okay. So I'm not going to write down everything. Okay. So that's green function, and this can be just write down as the space-time representation of the 2 pi to 4 plus I epsilon. Like this. So like this. Here I assume this is the vector, 3 vector. The space-time version. This is space-time. This is space-time. Sorry, space version, three space version, and this is space-time innovator. That's what we learned. Okay. Now, the quantum physics, something interesting happened. In quantum physics, QFT in curved spacetime, you can take some other orthonormal or like a positive energy mode. So if you introduce one like an orthonormal mode or positive energy mode, one can introduce another one, another basis, which called phi prime of I of x, and which is alpha ij, j of x plus beta ij, and phi j star of x, like this way, and j, and its conjugate is something like you just need to conjugate. It's just conjugate. Like this one. So the other case. So this is called some other basis. No, this is some other basis for positive energy mode, and often it's called Bogoliubov transformation. So this phi I also this phi prime also should obey this rule. This delta ij and so on. So orthonormal condition. This phi prime also should obey this orthonormal condition. So that of course I mean this phi prime and phi prime j prime star is equal to 0 and so on. And then I'm not gonna write down everything. Phi prime star is some delta function with up to sine phi j. I don't know. Okay, so those conditions will tell you that this coefficient has to satisfy the following condition. So this one, I mean, there's one more homework left. This is the I'm creating one more homework. I'm sorry about it, but this is the exercise for you to derive. So this is the dagger alpha minus beta t beta equal to 1 alpha dagger like this way. So this is derived like this derivation. So this is the homework last problem. It's very straightforward. Okay. So under the inner product, this alpha, so this alpha and beta is called Bogoliubov. By the way, Bogoliubov is coming from which country? Russia. Yeah. Soviet Union. I don't know, to be honest, currently which country is kind of.
His surname like a Russian.
Okay, maybe okay. But anyway, so let's not talk about this. Okay, I please search in the Wikipedia. Actually, he's kind of big shot in Soviet Union. Soviet Union. In quantum theory. But I heard that there's some institute in Ukraine, the Bogoliubov Institute. I thought he can be Ukraine. I don't know which one is correct. Just tell me if you find the correct answer. Okay. Anyway. So inner product of ij can be explained by this phi j. So I mean, since we expand this phi prime as a phi and phi I and phi star, I mean, if you take inner product, I mean, this inner product only see this guy, only this guy, and then the inner product does not see this one, so that just alpha is gone, so this is okay, and so on. So I mean, it's just a simple exercise. I mean, it's just a very simple, like this. And the star, one can just take a star, but I think it's too easy for you, so I'm not gonna write down two more. Okay. So using this one, so one can just show that the A prime of I is sum of alpha ij. Okay, like this way. Like this way. Okay, so there's a transformation from. So if you have the other basis, one can again define creation annihilation operator by using the linear combination of the other set of creation annihilation operator. Okay. So therefore, the vacuum is now different. So the vacuum in new mode is defined by like this way. Okay. So therefore, 0 prime is not equal to 0. Okay. So vacuum, which is defined by the creation annihilation operator, is different from the vacuum defined by new mode of I prime j. So that's a key point. So for instance, if you just do the expansion, so if you just consider the numbering operator of this new mode, which is the new vacuum, and numbering operator is the previous one, AI, AI, 0 prime, okay, like this one. And then plug this one, so if you do the inverse transformation of this guy, okay, but any case, it's okay. You can go to like this way. It's also okay to do like this way. And plug this guy into here. Then what you get is that 0, and use this one. So alpha star, I'm not gonna write the indices. Beta star a dagger minus beta a plus, oh, what I'm doing. So it's opposite. Sorry. E, sorry. Okay. Beta a dagger. What was that? Plus alpha a. E, sorry. Dagger. And 0. What I'm doing here? Oh, sorry. What I'm doing? Sorry. So alpha star a minus beta star a dagger. Okay. So that's okay. Okay. So now, so I just plug this one into here. So then, so what you see there first, I mean, annihilation operator just kill this one. So this one you don't need to consider. What's left is this guy, after creation operator, what you need to act is the also this can act on the like if it is unitary theory, this one can only act on here. This one is gone. So what's left is that the so like this. Okay, so that's the case. So therefore, if you just consider the previous vacuum, original vacuum, and sandwich by new numbering operator, you see that there's some non-trivial amplitude, So there's some particle creation. This means that even though the previous vacuum is just a vacuum, but if you use the new set of the creation annihilation operator to define a numbering operator, this number sees some particle. That's what it means. So this is called the Bogoliubov transformation. And using this one, we will show Unruh effect after the break. So let's take a break. Before taking break, so 3 more lectures are left. And I don't plan to do the exam, but I just give you one more homework, which is due in 2 weeks. I think it's okay. It's fair, I guess. I think I'm not gonna give you so much demand. Anyway, so I'm not gonna do it. So 3 more lectures, and the next lecture this lecture I will cover Unruh effect. Next lecture, Hawking radiation and beginning of information paradox. I don't know 2 more lectures left. So what do you want me to talk about? My plan is something like a recent development of like a page curve, something like that, or something like a what else? Page curve, something like what I'm talking. Maybe ADS Brown-Hanot stuff. ADS 3 CFT 2. This is Brown-Hanot stuff. I don't remember Hanot stuff. What else do you want me to talk about? I just thinking about what kind of topic I should cover. Is there some other candidate? I mean, something what I want me to explain. Just let me know.
2 more lectures.
Yeah.
Can we just grab Kermetry? We will just skip it, right?
Kermetric derivation of Kermetric.
Is it enough to lecture or not?
Okay. It's going to be a horrendous calculation.
Yeah, that's why I'm asking.
Okay. Derivation of Kermetric.
It's after that.
Okay.
Because I haven't seen the derivation in any lecture so far.
Okay, derivation of Kermetric. Or if you have some other some other think what I want. If you want me to cover, just let me know. But it should be related to something about this course. Continuation of previous year or something like that. What else I talk about? Something about the information paradox is also okay. Anyway, if you have something in your mind, just let me know. Okay, so let's take a break, 10 minutes break. Yeah, and if you have some suggestion, like I don't know, so I plan next semester there's a course at SEMIS called Black Hole. SEMIS will be taught by Hammett. I don't know. He's more expert than I am, so maybe it's better to take his course. I don't know. I think it's going to be official even at Fudan. Some of the SEMIS course become official Fudan course, so you can really join. But I don't know if Hammett continue to teach black hole. I'm not sure this course will be.
Will it be in English or in Chinese?
Of course, he cannot speak Chinese. so it'll be English. It's called Black Hole. I don't know what he's going to cover. I'm pretty sure there's some overlap with my course, but anyway, we'll see. But anyway, so I set up this course before SEMIS was born. So I didn't know there's such a so many courses will be open at the semester. So I don't know. But in future, I would occasionally teach this course most likely. So if you have suggestion or like some opinion, whatever comments on this or some complaints about this course, just feel free to tell me. From which I can change or improve my course in future for future teaching. Just feel free to tell me, just honestly. It doesn't. I don't mind. I really don't mind. Even if you complain, it's totally fine. Yeah. So from next semester, many courses will be available even for food and space students at semester. I'm pretty sure some of them are way better than the usual food and courses. I'm pretty sure. Yeah, so yes, so this is BTC black hole. Story of BTC black hole. BTC black hole. Yeah, and Slava told me that what else? And I'm like, yeah. He also told me curse CFT correspondence. But that's too advanced. I'm not so familiar. We'll see. Okay. Then shall we review? Okay, good. Fine, so let's get started. Now let's resume. So Unruh fact. Unruh fact. So Unruh fact is considered linear space let's consider the linear space. B and U, and then here we have the linear space, something like this way, and we just we consider the so this C, and this is R, and I call it L. So this part is called right linear wedges. This is called left linear wedges. Anyway, right linear wedge and left. And this is this observer C is the kappa B del B minus U del U and delta U, and this is just time vector. Okay. So this is called linear observer. Linear observer. And notation is something like a ds. The metric is the Minkowski, capital du dp is equal to minus dt squared plus dx squared. Okay. And v is equal to t plus x. Okay. And the Klein-Moore equation. So this is Minkowski space. So minus delta square plus del square del x square acts on the phi of x. This is a Klein-Moore equation. So therefore, it's a very, so if you write down this equation by U and B coordination, what does it become? How does it become? So I want to write down like this way. I use this del U and del B to rewrite this equation. How does it become? Yeah, actually, this is the case. So this is equal to this one, up to plus minus sign. Del U and del B is in fact the Laplacian, or plus minus. I don't know which one is correct. Plus, most likely minus sign, most likely. So therefore, the Klein-Gardner solution is a factorized form. This is the factorized form. So it either only depends on U, either depends on B. If this is the case, if B will see this guy, but you don't see this guy, you derivative don't see this guy. So therefore you get 0, and so on. So this is very similar in the, this is that's why it's you have a 2D CFT is a holomorphic. So this is holomorphic, anti-holomorphic. Anyway, so it's the same thing. And then, so what's the positive energy? Energy mode? Positive frequency mode. Positive frequency mode. E to the minus I omega t. Okay, like this way. So where P like this one. So this is the solution of this Crank-Gordon equation, as you can easily see. And then, since the u is t minus x, so therefore, when p is positive, you can just write down like this way, So this is called right mover. And then when p is negative, you become omega times t plus x. So therefore, it can be written v coordinate. So therefore, you have this one. So this is the, what was that? Right moving, and left moving. Okay. Now we want to understand what's going to happen in the x and y coordinate. So u is given by minus. Okay, and then we just rewrite. So this is x and t coordinate. So this here, x is constant is something like this kind of diagram. X is constant is something like this one. Okay, and t is constant is something like this one. T is constant. So, okay, so this is t constant. Small x and t. So this is the capital X and T. This is a capital one. And then we move on to capital small x and t. Okay, so the Crank-Gordon equation is something like so the metric here is ds squared is minus kappa x squared dt squared plus dx squared. Like this way, so it has something non-trivial here, so you have to be careful about the derivative. So 0 is equal to del A, and then phi, this is equal to like this. Okay. Here, phi. Sorry. So what is sigma? So here I assume that phi is proportional to e to the minus I sigma t of f of x. Something phi of x. Phi of x. Like this here. Phi of small x. Small x. So then the t derivative will c the sigma squared. So from here, so one can show that the phi of this one is e to the minus I sigma t and x I p, and the capital P is equal to plus minus sigma over kappa. So like this one. So this is a solution. I will just plug this one into here. What you get is that the so if you plug this solution into here, what you get is that the IP x IP. So once you do the derivative, you get a minus one, but you just multiply x, you get the original one. But in derivative, we will just pick IP part. And then again, if you apply for this derivative, you get the p squared minus xip. And if p squared satisfies this condition, this cancels with this one. Okay, is it okay? You get the solution. Fine. So therefore, so one can just consider again the right and left moving solution in the linear space. And here x and t are only defined in this right like a linear wedges. These wedges are only defined, and I call it, this one is R right linear wedges, left linear wedges. And then here one can consider right linear wedges. The basis is coming something like this one, e to the minus I sigma t minus capital P log x. Okay, so that's the solution. So I just rewrite this one by using log of x. Capital P is like this. Just rewrite it. Okay. So now, and of course P is equal to kappa, sigma, and kappa are related to kappa like this way. Okay, so then so let's convert this one is a classical type coordinate. So recall that this way. So this one is equal to u and x and t. So therefore, maybe one can just write down log u log minus u is equal to log x minus kappa t. That's easy to see. Log b is equal to log x plus kappa t, like this way. So this. And we know that the sigma and the kappa are related to like this condition. Okay. Sigma and p are related by with kappa, and here we have a log x, and then if you relate sigma as a kappa observer p, so one can use these coordinates, log u coordinate, log b coordinate. And then so up of r is equal to and then e to the I sigma over kappa minus u like this way, and this is p is 0, this is right mover. Like this way. So here, so recall that this is the u direction, this is u direction, and this is b direction. So therefore, this right linear wedge is, so recall that this b has to be positive, u is negative. So this is the case. And here left is the opposite. U is positive. B is negative. Okay. So therefore, in this capital, upper R means right linear wedges. Right linear wedge. It's only defined in this region. So therefore, So these these positions are left one. Okay. So it has to be here. Okay. So these are the basis of in basis in R, and then we can do the same thing for left. Okay. So now, not only this one, so we can just use the U left of P, which is the following one. The CP is equal to E to the I. So the sigma over kappa log U. And then, so this is U is greater than 0, U is less than 0. Because I mean, U and B are related by, so they are related by, how to say, U goes to minus U, and B goes to minus B. So therefore, we just essentially have you just implement this condition, CP and E to the minus I sigma over kappa log minus B. And then this is B is greater than 0, and B is less than 0, and P is positive, and P is negative. Okay, so those are the solution we consider. Okay. And then, so we just write down. So they form some complete basis. So the phi of x, if you have phi of x, one can just write down sum of k and b p r u r p of x plus bp of l u p l plus bp r dagger u bar r p of x and plus bp left dagger u bar lp of x. Okay. So those are sorry, I think I'm writing something stupid. This should be capital P. Okay. So those are mode expansion of the field. So here, these are annihilation operator. These are annihilation operator. So these are annihilation. Operator, and these are creation operator, and these the other are just mode expansion. And then seems I hope there is no typo in my lecture note. Let me check. Yeah, it's okay. Okay, so that's the case. Fine, and then so we just want to see how this modes U and this U mode, which are defined in only like these linear wedges, are related to the mode, which are the solution of, where was it? It's not written, I already erased, of this usual the mode for the phi t square plus phi x square of phi equal to 0. So here what we saw is e to the minus omega u, e to the I omega b. These are positive energy mode we saw. So we want to see the relation between this mode and then this U mode. So that's so essentially we want to see the volume of transformation of the between these two modes, two kinds of modes. Okay, to see that we need some criteria that we really have a positive energy frequency on U. Okay, so positive energy mode in U. In U can be obtained as follows. So just consider that f of u has the following Fourier transformation: d omega over 2 pi, and the e to the minus I omega u, and the f tilde over omega. Okay, and f tilde over omega is equal to the u. This is a dual Fourier transformation. Okay. So if you consider like this way, okay. So now, then just can consider this minus infinity to infinity, minus infinity to infinity. Okay. So for instance, if you have just simply you have e to the I omega or whatever u0, then the f tilde is something like a f. Oh, sorry. What am I talking about? So sorry, omega 0 u. So this is the one basis of positive frequency of this equation. Positive energy mode. So this is the case. Then f tilde is what? F tilde omega is what? Fu is equal to this one. Ft is what? Delta omega 0 minus omega 0. Okay. So you have so u is okay. F of u is something like a just wave function, just normal like this kind of function. But if you do the Fourier transformation, it's just delta function at the omega 0. Okay. That's very what you learn in Fourier transformation, the Fourier transformation basic one, right? It's okay, right? Okay. But if you have a superposition, or if you want to have a superposition of frequency, we can have something like what was it? We can have something like a more like an amplitude like this way. You can have like this f tilde. So this is f tilde of omega is something like a f tilde is something like can have like this way. Okay. Is it okay? And positive frequency means that so f tilde of omega, this part is 0. Positive frequency means so omega 0 is kind of omega is energy. So therefore the f tilde of omega has to be 0 to have the positive energy mode, but the f tilde of omega positive part can be non-zero. For instance, one can take like f tilde is something like this way. This is kind of like considered as the superposition of positive energy mode. Do you understand what I mean? Okay. But if you have the chunk like this way, wave packet or whatever you call it, in the negative energy mode, it's no longer it's impossible to not to include the negative energy mode. Okay. Anyway, so it's just the Fourier transformation lesson 1. Okay, so to have the positive energy mode, we need to have f tilde to be f tilde omega 0 amplitude has to be 0. Okay, so for this is essentially the necessary condition. Positive energy mode has to be like this way. Okay. Okay. And if f of u is analytic in lower half plane, so f of u, so this is u, u plane, and we can just take contour from minus infinity to infinity. So I'm talking about this integral now. So minus infinity to infinity. So here minus infinity to infinity is this contour as minus infinity to infinity. But if it decays, if it decays on in the here in the very big R, so if f of u is very small, goes to 0 when along this direction. When R is very big, R goes to infinity. So one can take this contour to get the f theta equal to 0. Omega is 0 for 0 for omega to 0. So let's think about it. So here, if u is analytic here, so if you just do the contour integral of this one, there's no pole. So therefore, one can just set this one is equal to 0. Okay, and there's no contribution from here, f of u, and then omega is negative, u is here it should be. Just a moment. Yeah, so it's okay. So here, if you take contour in lower half plane, and then so since the red part is the contribution is 0, once you take r goes to infinity, so therefore from here to here you get the f theta is equal to 0 once you perform this integral. So therefore you can just get this the positive energy mode. So this is one criteria one can use to pick the positive energy mode. Okay. And to use that one, we would like to create some positive energy mode by using this U and UR and UPL. Okay. So form the positive energy mode by using so this is R, sorry. And this is R. So we just do the following transformation. So L of P is equal to Cp e to the I sigma. Okay, unfortunately I have already erased it. It's written there. So it's written there. Kappa log U. Okay, so this is the when P is positive and U is positive. Okay, U is positive, and this can be just manipulated. Cp is e to the I sigma over kappa log minus U plus I pi. E I pi. Or plus or minus, I don't, yeah, minus I pi, log U. Okay, so do you understand this transformation? Is it okay? So here, I just put the e to the I pi minus U. This is equal to, U is equal to minus e to the I pi U, right? Okay? Is it okay? My e to the I pi is, okay, maybe minus. E to the minus I pi is equal to minus 1. So therefore, minus 1 times minus 1 is 1, which is equal to this plus 1. So therefore, U is equal to this one. Okay? And do the expansion in terms of log, you get this one. Okay? Is it okay? And this can be written as follows. Cp e to the pi sigma over kappa e to the I sigma over kappa log minus U. Okay? Log minus U. That's
U is not positive here, right?
U is positive because I pick, sorry, I think I missed bar here, sorry. I picked this solution.
Log minus U.
So minus U is the, minus U part is the UR part. So that's exactly the point. Our P is equal to Cp e to the I sigma over K log minus U. So that's the case. So this is P is positive and U is negative. Okay. So here now I'm talking about this Unruh case. And this is R and left. And U is negative is always right part. And U is positive is the left part. Okay. So therefore U is positive is really coming from left part. Okay. So this part. And then U is negative is right part. Okay. And you can combine them together. If you combine them together, you can, to combine them, there is some up to factor. So there's a factor here, up here. So therefore, you have to multiply this one. So U, P, the R is equal to plus e to the minus pi sigma over kappa U bar L over P, which is Cp is e to the I sigma over kappa log minus U. Okay, so this is another function which is defined by both L and R. Both L and R. Is it okay? So if you compare these two modes, the difference is only here, only appear here. This is defined in left radial wedge, This is defined right in the wedge. I want to define both of them. To do that, you have to multiply this factor minus of the inverse of this factor, and add them up. Then what you get is this one. So this is all defined. P is positive, and U is everywhere. U is both positive and negative. Okay. So this is one mode which define L and R. Okay. And then one can analytically continue in the whole plane, and which is only depends on you. Okay, which only depends on you. We can do the same thing. If you do the same computation, so if you only look at, unfortunately I erased, if you go to look at the P goes to 0, and if you look at the same combination, you PR plus E to the minus pi sigma over kappa U bar L of P sub P, and then what you get is as follows, the CP. Kappa log minus P. Okay. So this is a P goes negative one. So recall that the U bar L is something like a CP e to the minus sorry, what I'm doing here? Oh, sorry. Sorry. E to the minus I sigma over kappa log minus P. Okay. So recall this one is equal to Cp e to the minus I sigma over kappa log minus P. But this guy is Cp e to the I sigma over kappa log B. Log B. And then most likely you have to multiply minus sign. Minus sign. Okay. So this guy is this one, and do the same trick. So just write down B as a minus e to the what was that? Most likely minus I pi B. Just do this expansion. Just replace and then log expansion to get this factor. This factor. Okay. Yeah. So P goes it's negative. You just have this basis. And then we can do the same basis. One can just create. So UP L is equal plus e to the minus pi sigma over kappa U bar R over P. So just creating a new basis for the linear space. Cp e to the minus pi sigma over kappa e to the minus I sigma over kappa log minus U, and P goes to 0. And Cp and e to the I sigma over kappa log minus B, P less than 0. So like this way. Now, so we just pick the new set of positive frequency. This is U. New set of positive frequency mode as follows. With this one, and then this one. Okay, so here both are defined as it only depends on u and b, u and b. So therefore, it's a solution of Klein-Gordon equation. And if you analytically continue it to everywhere in the linear space or Minkowski space, it's totally okay to be this complete set of the basis of the Klein-Gordon equation. These. So I call it, so this Cp is just a normalization constant. And I call it this one up to factor, so this times some normalization constant dp is equal to, I define as a bp1, and this one times dp, maybe 2, 1, is equal to bp of 2. So these are a new set of solution. And And by using this, the property, one can show that this new set of B complete basis of positive frequency. These modes are in fact analytic in the lower Hawk plane, so that these are positive frequency. So now we have a new set of the positive frequency mode. So therefore, the field can be defined as follows: Bp of 1 plus AP 2 Bp of 2 plus AP 1 dagger of B bar P 1 plus AP 2 dagger Bp of 2, and the sum over P, like this way. The previously, previously. So I just write down the other expansion, which is sum of B, and it's written in U mode, U and the creation annihilation mode of B, right? So the previously we have this one, B1R, URP, plus BP, L, ULP, plus its conjugate. So you have a two set of expansion as we desired. Okay, and then so this B are written all like capital U and capital B, and then you just can analytically continue it to the linear space. So therefore, it's easy to satisfy this U, and then this B is equal to phi, or Bp I to be 0. Okay. It's easy to satisfy. Okay. See that they are satisfied this equation. So therefore, the Minkowski vacuum can be defined AI acts on P is equal to 0 for any P. So this is, so therefore, I call it, this is a Minkowski vacuum. Then we just do the expansion in terms of how this creation annihilation. So this is annihilation operator in Minkowski space. Annihilation operator in the, how to say, Lindler space in R and L. R and L are given by this B operator, and the conjugate one is there's a B dagger here, and B dagger here are the R and L, and of course P and P here. These are the creation operator, and we just want to see how they are related. Okay. So this normalization constant. So I think I'm not going to go into detail. So it's very easy to determine the norm of this B1. So norm should be equal to norm of UR P and URP. And from here, you can just easily determine that the normalization constant of P, so this is I. Normalization constant is given by e to the pi over 2 kappa divided by square root. I think there must be sigma here. Sorry, there's a typo here. Square root 2 sinh pi sigma over kappa. Okay, so you can just determine this normalization constant by just taking the appropriate the normalization of B and U should be equal, and from there one can just show that the B R of P is the inner product of R and P of phi, which can be written as follows. Kappa sigma over kappa e to the pi sigma over 2 kappa BP of 1 of phi minus e to the minus pop sigma 2 kappa of B bar 2 of P phi, like this way, like this way, like this way, like this way. Okay, so that's what you can show from so the relation between U and V. So U and V are, so yeah, we call this is B1 and this is B2. So therefore this one, and then if you do the inverse transformation and B and U, you can just write down U in terms of B, like this way. And take inner product. This will give you, of course, this will pick, of course, this guy, and then this will pick this guy. So therefore, this is equal to AP of 1, and this is equal to AP of 2 dagger. Okay. So therefore, this will give you a relation between B and A. Okay, B and A. So now, we just want to evaluate the following. So 0, Minkowski vacuum, and P, R, and Minkowski vacuum, and which is 0. Dagger, BP, R, Minkowski, and plug this relation into here. Okay, we know it only see this square, right? So this used to be it's called alpha, this called beta, and what you get is beta square essentially, up to this normalization. Okay. And if you do this computation, what you get is that the this is equal to e to the pi sigma over kappa minus sine over 2 sinh pi sigma over kappa 0 Minkowski a 2 p a 2 dagger p 0 Minkowski. So we just pick only I just square this normalization beta here, and then what's left is AP dagger and AP. Once you sandwich in these two. Fine. So therefore, this is equal to so this is equal to zero m and p r 0m is equal to 1 over e to the 2 pi sigma over kappa minus 1. Okay, so that's the case. And then now you're familiar with this. This is the Planck distribution. Of the with temperature is given by kappa over 2 pi, and then if you restore all the constant, it should be h bar here and kb here is this. So therefore, this means that this 0 Minkowski vacuum observed by Rindra observer is no longer will receive some thermal states with temperature with the given by surface gravity divided by 2 pi. So that's the computation. So what I did is that they just do the base change of a Klein-Gordon equation. So one is this given by U operator. U is only defined right and left, but one can combine U R and U left in nice way, which is analytic all over the Minkowski space, which is called V. Okay. Then they do the quantum field, Klein-Gordon field, by just do the model expansion, two different model expansion. But we know the relation between V and U, so that we can give a relation creation operator, annihilation operator, A and V. Okay, so this creation operator, annihilation operator, we can just relation which is given in this way, and then if you just take the so-called expectation value of the numbering operator in right Rindra wedge with the sandwich by Minkowski vacuum, you get some Planck thermal distribution. So that's the consequence. So this means that so this Rindra observer will feel like a thermal state, even though at the horizon. Thermal states. So here, so what we have is something like this one. And the Rindra observer is what we are considering something like this one. So really like close to the horizon here, and now because of the something like there you will see some thermal states when you accelerate here. So that's the computation we did from the Bogoliubov transformation. So important thing is that this Rindra observer has acceleration at the acceleration which is the copper, measured by copper, which enters in the this thermal states temperature. And moreover, so the Reynolds, if you just recall a Schwarzschild metric dt square, sorry, plus, and this inverse dr square. Okay, so this, and take the zoom in the r is equal to, I don't remember the detail. If you zoom into near horizon limit of the Reynolds space, you will get the exactly the same metric. R minus 2 to m is equal to x square 8m. So this is ds square. The Schwarzschild metric of the most important part of Schwarzschild metric will become ds square is equal to minus kappa x square dt square plus dx square. What's the value of kappa?
For Schwarzschild,
Yeah.
1/4.
Yeah, so this kappa is in fact 1/4m. 4m inverse. Okay. So if you zoom into the near horizon limit of the Schwarzschild like this way, the metric becomes like a Reynolds metric. So therefore, we assume we also like expect there is something thermal thing going on even in the Schwarzschild black hole. Okay? So that's the expectation. And since you get the thermal states, I don't think I have a time. But since you have a thermal state, so Planck told us that if you consider the trace of this if you consider trace of L of this Minkowski state, trace of L is that all the states on here, left linear wedges, all states are summed over. Okay, all states are summed over in here. You will get e to the minus beta h hat right Hamiltonian sum over e to the minus beta h hat r sum of where beta is equal to 1/kappa b temperature, which is the 2 pi kappa b divided by h bar kappa. So that's the case. So this is the statement of this what's going to happen. So if you just sum over all states of L of this Minkowski vacuum, you get the thermal fraction. Thermal Hamiltonian, or Boltzmann weight of the Boltzmann weight in HR means right Reynolds wedge. And I don't think today I have a time. If you just do the correct calculation of this Minkowski vacuum, so Minkowski vacuum can be written in some coherent states of right Reynolds wedge and left Reynolds wedge, like this way. With some number f of n. So there's a coherent states we can just write down. So therefore, you can just consider some density metrics. So this is called density metrics. Density metrics of the 0, m. This one will be, I will review later, next class. This can be written as the following: sum over n equal to 0, infinity product of p e to the minus beta en sum over e to the minus beta en n p n p. Like this way. Sorry, I think I should write down this is nr p nr n and p. So this is right. So somehow Minkowski vacuum can be written as some entangled state of right and left. This is left. Right and left Lindner states, and it's moreover coherent states. And if you take density matrix, some trace over all left Lindner states, this density matrix is really like a Planck thermal distribution. So this will I will derive next time. Anyway, so this will I will derive next time. So, but in any case, so this is not Minkowski vacuum is no longer. I mean, vacuum. It's just really coherent states, in terms of right and left window states. So that's what I want to explain. Okay, so let's review next time this part and move on to Hawking radiation. Okay, let's go through. If you have a question, just tell me. No.